No quieras.
Qué poca audiencia.
No quieras.
Qué poca audiencia.
No quieras.
¿Por qué se repiten las cosas?
Quieras.
Hay como...
Jolas con. Ya está. No quieras.
Tal vez soy yo el que está repitiendo. Sí.
Si tienes el volumen como...
Un poco, sí.
Bueno, vale.
Bien, ahora.
Vale, sí, yo ahora lo hago bien también. No se repite. Bueno, vale, pues empezamos. Ya sigue uniendo a la gente. Estará bien tú. ¿Ya está grabando? ¿Qué? Bajando. Luego lo corto.
Adelante.
Well, it's my pleasure to introduce you to Antonio Hales, who is a Chilean astronomer and also my friend. He completed his PhD at the University College in London in 2007, and after a 2-year postdoc at the National Astronomy Observatory in Virginia, he moved to Chile to participate in the commissioning of ALMA. He stayed there as a scientific permanent staff for 15 years. Yes, part of the Department of Scientific Operations, and then a year ago or so, he moved back to Virginia, to the NRAO headquarters, where he is now deputy manager of the North American ALMA Relevance Center. Well, his research is focused on understanding the origin, the formation of planets from the early stages of the protostar. So he studied the evolution of the dust, the gas, the protoplanetaries, using both simulations and observations. He used aerodynamical and radiative transfer models. Apart from this, he's also very deeply involved in other projects like educational projects, outreach projects, projects that involve art and science. He's the one behind the ALMA Sounds, where he gathered a lot of well-known music producers to interpret the spectrum of Orion. And he's also the author of, I don't know if it's 1 or 2 children books, and responsible of a program to increase the involvement in astronomy of underrepresented communities, etc., etc. No? He's deeply active in a lot of different projects. Well, today he's gonna talk about my studies of young eruptive stars. He was visiting Madrid like a couple of weeks ago, 3 weeks ago, but we scheduled his seminar the afternoon before 5 days bank holiday, so we had to cancel because he wasn't gonna have the audience that he deserved. So, Antonio, whenever you want, the floor is yours. Thank you for coming.
Thank you very much, Patricia. Thank you very much for this very nice introduction, and for the invitation to come to Madrid and share our latest results on ALMA studies of eruptive stars. I'll be speaking for almost an entire hour about this. Thank you, Enrique, also for accommodating this change. I'm really excited to be here, finally sharing this. I think we tried to schedule this talk for 2020 during the pandemic, but we also had to reschedule that. So it's a real pleasure to be finally here in front of this lovely audience. As Patricia said, my research is focused mainly on star planet formation. So just to put in context, this is the well-known paradigm of star formation, in which stars form from clouds, collapse, etc., go into this protoplanetary, further class 1 phase where the star and the disk are still embedded in the envelope. Then you start dissipating the envelope. The star starts to become optically visible around 500,000, 1 million years, and then we go into the planet formation phase that we all know ALMA has been an excellent tool to diagnose what's going on in these phases and then eventually evolve. So in this talk, we'll be mainly focusing between the C, D, and E phases here. We're trying to understand precisely at which moment stars build up most of their mass, planets begin to form, and how that process starts shaping the future architecture of the planetary system. And well, as I mentioned, the title is about eruptive stars, and today we think that eruptive stars are young stars that are undergoing bursts of accretion. That's how we understand this phenomena. Okay, and today we believe that episodic accretion is key in the sense that they allow stars to accrete a significant fraction of their total mass. It gained a lot of interest after Spitzer because it came as a savior to solve the well-known luminosity problem, in which protostars, if you measure them, they were underluminous compared to the predictions from steady-state accretion. It's also believed that these bursts of accretion can drive the evolution of the disk material, changing the properties of the dust grains, the disk chemistry, the recondensation of ices, and in turn, planet formation itself. So here on the top left, you're seeing the famous light curve of Ephuriori, the first eruptive star that was discovered. In the middle, you have another star.
You are not sharing your presentation.
I'm not.
No.
Armando?
I thought it was.
I can see the presentation. I can see it. Yeah, I can see the presentation.
I can see it. Sorry.
Yeah, I could see it. I mean, you were saying, yeah.
Sorry.
Enrique, can you see these plots I'm talking about now?
No.
No?
Well, it's my problem.
Okay.
Well.
I'll go ahead then.
Yes.
Okay.
Sorry.
So the first two plots here are light curves of Ephuriori stars, and in the bottom one is a result from Peter Abraham with a VLT, in which they observed one eruptive stars in quiescence and during the outburst, and they saw how during the outburst the stars got more crystalline, resembling more what we see in comets in the solar system, in which we know they have been very many times reprocessed by the sun. So in this context, I wanted to give you a little bit more of a historical background of how things happen. This is Orion, as you well know, seen in the optical. And we're going to zoom into the shoulders of Orion in the Lambda Orionis region next to Betelgeuse and Bellatrix. As you know, if we switch into an infrared, the story changes. We start seeing all these warm clouds where stars are forming. And if we zoom into Barnard 35, that is where we're going to find Ephuriori, the first prototype star that was discovered to suffer these sort of bursts. It lies within the LBN 879 region, and Ephuriori is the bright source at the bottom right that is surrounded by this reflection nebula. So it was Ephuriori who was first discovered almost more than 80 years, I would say 88 years, since 1936, when it went into outburst. The star became 7 magnitudes brighter than it was originally known. And it was a very, very quick phenomena that was poorly understood at the moment. It was Dr. Dorit Hofstede from Harvard. She was doing her PhD at Harvard at the time, who gathered the light curves that were later published in 1955 by Wegman, in which he's describing this weird phenomena on Ephuriornis. But after that, for many years, this was forgotten. It was never understood. People actually at the time thought this was a nova. And it was actually Herbig who in 1966, he said, okay, let's go back and restudy this star and try to understand what is going on. But for many, many years, as I said, this was the only star that was discovered. And we'll understand, I hope you'll understand in this talk why. But after that, and throughout the decades that followed, we have discovered many, or let's say 2 handfuls, 2 dozens of those, not that many, Ephuriori-type stars that follow the same sort of photometric behavior that was first discovered by Ephuriori. Here you can see in the top right the discoveries of the well-known ephemeris until the 2000s. So what characterized this family of stars is that they suffered strong changes in their magnitude, over 5 magnitudes increase, which correspond to over 1,000 times increase on the accretion that the stars is undergoing. And these bursts can last from years to decades. As you can see in the bottom right, you are seeing here the top 3 light curves are from Ephemeris type stars. They were all named after Ephemeris, the prototype. And the 2 bottom ones are what we call the X-Ori type. And I'll talk a little bit more about them, but those follow less intense brightenings and less long in terms of their duration. They have also strange spectroscopic characteristics. They saw when they were trying to understand Ephemeris and the other stars that were subsequently discovered, they were trying to fit spectra to these stars to see what kind of stars they were, and they couldn't, because they would resemble cooler stars. You could fit the blue part of the star with the stellar spectra with the early type star, but the cooler part of the spectra, sorry, the redder part of the spectra, you had to go to cooler stars. So they didn't really understand what was going on. And they also noticed that some of these stars had double peak absorption profiles. So with all this in hand, George Herbig said in the 60s, okay, I'm going to go and understand and try to understand what's going on. So he started dismantling the different hypotheses that were postulated. So the first idea is, what is this a nova? And people say, no, this is not a nova. Novas don't behave like this. They don't have the spectra, they don't have this photometric behavior. So he said no. So he said in his early papers from the 60s that this is probably a rarely stage of early stellar evolution. That's the vague understanding that he had at the moment. And then with these other people, particularly Petrov in Russia, started working with Herbig in trying to understand this as a bloated star, okay, a rapidly rotating inflated star with a spot. And they said they could explain some of these theories, so some of the observations with this theory. But it was actually the Harman with Scott Kenyon, who in the early 80s and the 90s came with what is now believed to be the proper explanation for what is a Ephemeris type star. And Ephemeris can be explained by a star that is submerged in a superheated accretion disk. And because they are submerged in this superheated accretion disk, we're not seeing the photosphere of the star, at least during the outbursts. We're seeing the disk photosphere, okay? And this explains very well the spectral energy distribution, the increase in brightness, and also the difference in line profiles. That can be explained by differential absorption, okay, by absorption of the stellar spectrum, or self-absorption caused by different radius to different regions of the star. So because the faster rotating parts of the star are closer to the star, they are hotter, and hence you see that part absorbed in the blue region. And then as you move towards outside the stellar area, you have cooler kind of absorption and also lower rotation. So the stars appear as if they were later type stars with lower rotations. They call this the great debate, but here you see Scott Kenyon, Harman, and Herbig, and Nuria Calvet having a very, very friendly conversation type discussion. And this is a cartoon representation of what I was trying to hand wave here. You have the star on the top having normal magnetic type accretion star into the star, and then you start having the disk going into the star, going inside the accretion radius, and eventually submerging the star and going into the outburst, which is what you see at the bottom. And this theory of the accretion disk model, as I was mentioning, is doing a great job in explaining both the spectral energy distribution and the spectral features that we see typical of Ephemeris stars, which is what you see on the right. Okay, here on the right, you see B1075 Cygni, the spectra, the double peaked absorption spectra caused by the differential absorption of different parts of the disk. And also in the bottom, you see the typical absorption of other type of stars compared to a disk model. Theories have also other type of characteristics that make them singular. They have Piscini type of profiles at very specific lines, which is indicative of very strong winds emanating from
Antonio, can you... No, vale. Esto que acaba de entrar es que hemos tenido un problema, está Antonio reconectándose.
Sí, porque a mí también se me ha desconectado.
Hola. Te congelaste y te desapareciste.
Interesting. Let's go back again. Can you see my presentation now?
Yeah.
Yes.
How far did I go before I froze it?
Further, let's see the slides. Yeah, it was there. Oh.
Okay, apologies for that. Well, this is the cartoon explanation of what is the accretion disk model, which is the current paradigm that explains the best all the observational features that we see in Fourier type stars. That is the spectral energy distribution on the right, on the left plot, and also the spectral features that I was describing earlier that characterize this type of stars, the double peak absorption profiles, and also the apparent cooling of the spectral type as you move towards the redder regions of the spectrum. Viewers have also other type of observational characteristics like Piscini profiles at very specific lines, which are indicative of winds, which are also consistent with the fact that the stars are having these bursts of accretion, which in some sort have to reflecting bursts of jets and winds. They also have reflection nebula that seem to brighten up during the bursts, as you can see here in the middle plot. You see B900 Monoceros, which is a Fourier type star that was discovered by Jim Toms, an amateur astronomer, by comparing his photos from different nights. At the center, you can see that on the left you don't see very much, and on the right hand you see this new reflection nebula that appear during the outburst. So, in terms of evolutionary state, Fouriers resemble mostly late class 1 stars, protostars, so stars that are still slightly embedded in their envelope, but some of them resemble more like class 2 protoplanetary disks because they don't have a lot of envelope surrounding them. And one of the main questions has been, what is causing the outburst? What is causing this instability in the disk that is triggering the outbursts? Things have become more complex with the years. We've discovered more eruptive type stars, and I was mentioning earlier, there is this second class called X-ORS, named after X Lupi, which was the prototype star that was first discovered. So she is the one with the red photometric light curve here on the plot from Harman 2016. It's a review that he published on eruptive star and on episodic accretion. And these type of stars are characterized by shorter and smaller accretion bursts. that sometimes can last days, sometimes weeks, but not year long as FURI type stars. And they also have SEDs that resemble much more class 2 protostars. So they resemble really classical Titori stars when they're not in outbursts. During the outburst, so they have emission lines, and they have the typical magnetospheric accretion that you expect from classical Titori stars. But what we see is that during the outburst, these emission lines brighten much more. The photosphere appears to be veiled by the accretion flow, and the timescales that we see, the duration of the burst, are more consistent with some sort of inner disk stability. So one of the theories that the material piles up near the inner rim of the disk, and suddenly it just gets funneled through the accretion flows, triggering this smaller scale outburst, to call it in a way. But now in Protostars and Planets 7 last year, and this there was a very nice review by Fischer and Agnes Kospal and collaborators, showing that now we see variability in many young stellar objects. And one of the challenges of this decade is trying to disentangle what are we seeing, because variability can come in many flavors, especially in young stars. So here in blue, light blue, you have the types that we associate to accretion-related events. So those would be FUORs and XORs and everything in between. And then you have other things like, for instance, extinction-related behavior, especially if you have envelopes, you have, and disk, you have extinction-related behavior that will be variable as well. And other type of phenomena that I won't get into too much detail. What is consensus today is that outbursts are now common. Systematic robotic surveys of the sky have supplanted the role of amateur astronomers in the discovery of new type of FUORs, XORs, or outbursting sources, and we're finding at the rate of 1 star per year, which is actually what you would expect if you do statistics in the galaxy, if these bursts are relatively short-lived compared to the age of a star. There was an optical bias originally towards the optical because people were taking photographic plates, but now, thanks to the surveys in the infrared and in the submillimeter, we're discovering this type of bursting phenomena even as early as class 0 protostars. So we've seen them in the infrared, as you see these MIPS plots, and also there's very nice work from Doug Johnston and collaborators using the JCMT to discover this type of stars. And we're expecting these rates to go much higher once the Vera Rubin telescope comes online. And if you talk to theoreticians, they're going to come out with 1,000 different ways of making the disk unstable. It turns out it's very easy to make the disk unstable. So I'm listing here some of them while letting play this animation by Edward Voloyov and Basu, in which you have a disk that is going to become unstable. You have in the bottom plot, you have the accretion rate. So it's very low, what you would expect of classical Titori stars. And sometimes you're going to have these jumps due to the disk becoming unstable and those instabilities traveling towards the disk and falling into the star. But that's one of the ways to render the disk stable. So I'm listing here many of them. There is disk fragmentation and sparkles, which is what you're seeing here. There is magnetospheric star-disk interaction. External perturbation is becoming a very trendy topic for explaining outbursts. There's super nice work done by Daniel Price in Australia with his group. There's a very recent paper explaining FURI in many scales. And there's also this idea that was put forward by Agnes Kospel, measuring accretion rates in the disk and accretion from the envelope into the disk, and looking for differences in those that could explain a piling up of material in the disk, and hence the trigger of an outburst. What is clear is that we need to probe the disk envelope properties before to be able to compare with the predictions from the theory. As you can see now in the plot, we've had like these very sharp spikes in accretion rates from the Voloyov and Basu models. Before ALMA, very few FURI disks had their disk resolved. This work by Laura Perez using, I think it was Owens Valley Observatory. And a special calibration technique, they were able to measure the size of the disk. They were able to resolve and also put an estimate on the disk mass. And it was the first results were pointing towards the fact that the disks were very, very low mass, contrary to what we have expected. And also surveys of a group of stars show that XORs were mostly undetected at the sensitivity limits of the pre-ALMA era. And it was with this motivation that in the early days of ALMA, with Lucas Chiesa, we put a pilot proposal for observing 3 FUORs and 5 XORs in Orion, and got we managed to resolve a few disks. We detected most of them, even the XORs, but it was very clear if we compared flux or mass, if you do the conversion, assuming optical lithium emission, that the XORs were less massive than FUORs. So you can see here on the plot, the stars on the top left are FUORs, so they are more massive, and the disks are relatively compact compared to a population of classical Titori stars, at least for stars of the same mass. Which is what you see here in red. The red plots are classical Titori stars. So some of the conclusions, as you should be, is that the FUORs are brighter than XORs, than class 2s, and also than non-eruptive class 1s. Now, we did some modeling, which is what you see here on the right, and what permeated from these models is that most of these disks are likely to become optically thick, even at millimeter wavelengths in their inner 10 AUs. Meaning that our mass estimates, assuming optical thin emission, are probably wrong, and the disks are way more massive than we believe, assuming optical thin emission. We followed up this work. This is a paper we published in 2020. We have been observing more stars systematically. Other groups have been observing more stars, so I try to put everything together in this plot. So triangles are FUOR stars. As you can see, they all lie above class 1s and class 2s in Ophiuchus. One has to be careful when comparing from different star-forming regions because they have different ages, but we believe here the comparison, at least for the populations, is valid. And you can see that the XORs like XLOOP and GM-CHA lie at the very bottom of this plot. This trend has been confirmed by other surveys, like the one that Hayu Liu conducted with the SMA. You can see in the bottom right, there is a cumulative distribution plot that shows that the population of FUORs and XORs is significantly more massive than the populations of classical Titori stars in different star-forming regions. So you have Taurus, Lupus, Chameleon listed here, and this seems to be the prevalent result. And so here you have also cumulative distribution of stars of different age in different regions. So you have class 0s and class 1s that are more massive than typical class 2s. This is what you see on the left of the top right plot. And the FUORI XOR distribution would lie somewhere in between class 2s and class 0s and class 1s, just to give some context of what we're seeing. We can get also different kind of mass estimates from CO isotopologues, which also allows us to compare with synthesis of disks and get a better estimate or a second-hand estimate of what we estimate from the dust, which we already know it's biased because we don't know the optical thickness inside the disks. In cycle 0, very early in the very early days, with only a few antennas, we targeted FUORI itself. I'm going to shift now into more specific into this system itself, the prototype system, FUORI, and pre-ALMA observations were pointing out towards an idea that the star was not surrounded by a big envelope. There was no outflows, at least detected in single dish spectra taken with JCMT by Neil Evans, and without knowing very much what to expect, we pointed ALMA, and the image on the right is what we got.
the disk seems resolved. Now, to add complication, FURI itself is a binary. You see the two crosses here on the right are showing the position of the two binaries. And in even this barely resolved image, we were able to put constraints on the disk sizes and on the possible disk masses. So we got an upper limit for the disk sizes of 45 AU, which is relatively small compared to the most known protoplanetary disks, and also by using optical lithium emission, getting masses of 10 to the minus 4 solar, 10 to the minus 4, 10 to the minus 5 solar masses, which is very on the low end of what we see in class 2 disks. So in 2012, we decided to take a closer look at FURI, closer than what we had done in 2015. And we got the high resolution images. I think it was configuration 9. ALMA goes up to configuration 10. So it was pushing the limits of what we could do at the time. And we got very nice resolved images of the two disks. See, so here you have, FURI North, so which the one we believe is the active star. That is the one that is optically visible. FURI South was only discovered in the mid-2000s, thanks, I think, with the VLT and with infrared observations, that we were able to see that there was a star. It's deeply embedded. It's still in a lot of material that we saw from the ALMA observations. And with this data, we were able to put constraints and do some visibility modeling of the data from each disk to constrain better the inclinations of the disks and also the mass of the disk and also the radius of the two disks. Both disks have the very similar radii of 11 AU, which is very small, but it's what you would expect if you have truncation due to binary interactions. By resolving the disk, we also managed to get a better grip on the inclination, which was actually just coming from models fittings to the disk models that were pushed forward by Harman and Kenyon. And by this refining of the inclination, also changed what was coming from the disk models, and we got to constrain the accretion rate to 10 to the minus 4 times 10 to the minus 5 and not 10 to the minus 4 as was originally thought in the first observation, the first modeling, so FURI itself. So don't need to go into much detail of the modeling. It was MCMC modeling that put strong constraints on the disk, but also the fact that the disks are small and they don't have a lot of structure puts strong constraints of the outburst mechanism, because many of these outburst mechanisms were postulating the presence of big spirals or big clumps that we don't see at this resolution. We have followed up a lot this system. This is a paper we published with Baobab Liu, in which he did an excellent job in putting together everything we know in terms of photometric observations of this, going all the way from the very low radio frequencies with the VLA, all the way up to the optical with gravity. And with this sort of modeling, we were able to fit different components that surround FURI. So here on the cartoons you see on the bottom, you have on the left FURI on north, which is the outbursting one, and on the right one, FURI south, which is not in outburst. And what is interesting and new from this result is this are the two green regions that you see in FURI at the center. Okay, and what is fantastic is that, and that you don't see in FURI south, is that the let's say dark green, which is at the bottom, FURI 4, I think it is called, that region is hotter than the atmosphere of the disk. So that's the opposite of what we see in FURI south, and the opposite of what we see in classical Titori disks, in which the atmospheres of the disk is what is irradiated by the star, and hence is the hotter part of the disk. But here, and in agreement with viscous accretion models, the center of the disk, the disk midplane, is hotter because it's heated by this viscous energy dissipation that is caused by the enhanced accretion rate. So it's a really nice putting everything together, making everything consistent for a priori and for a priori stars in general. A byproduct of the pilot survey that we did with Lucas Chiesa in the early days of ALMA is that we've discovered strong, I mean, very large outflows around all of these a priori stars, which resemble evolved class 1 type stars. And we didn't detect any outflow in XOR stars, which is consistent with them being more similar to class 2, more evolved protoplanetary disks. So here you have some images of what we saw. They are large and they are wide angle, which is consistent with stars that are more evolved. Let's say more evolved protostars that are already started dissipating the envelope. We did this other survey with a few more stars. We also discovered the same trend in the sense that the stars that are resemble more FUORs or are transitioning between FUOR and XORs have outflows and they're wide angle if you compare them to class 0 protostars. And putting them into context of other protostars, you can compare them to the survey from Hector Arce and Anila Sargent that show that as you increase in age, the opening angle of the cavity increases, which is what you see in this plot on the top right. Of course, there are some uncertainties, large uncertainties of the ages of the system, but ballpark, it's showing that everything fits together with this cartoon in which, as the stars grows, starts launching jets that in turn can sweep up some of the envelope material, and then you start having the stellar winds that continue to work, and eventually a combination of dissipative processes from winds and accretion will eventually dissipate most of the envelope material. FUOR itself from the early 90s surveys did not show any molecular outflow. We know that FUOR stars had molecular outflows from these works, early works from the Texomillimeter Observatory from Neil Evans and collaborators, but for FUOR it was a mystery because they couldn't detect any. However, you do see in this optical image taken by another amateur astronomer, Rick Johnson, you can see that FUOR is surrounded by a large reflection nebula, right? So there is some material there. And this is something that came from a recent result that we got with ALMA, this time using the 12-meter array plus the ALMA compact array, which is, as you all know, more sensitive to extended emission. We were able to detect 12 CO outflows, very similar to the in also very large scale, very large opening cavity angle, and that seems to trace very nicely the reflection nebula, as you would expect, right? If this is material that is being dissipated, swept out from the central star. This is a cartoon view of this, but obviously we need to call into more sophisticated theoretical models to try to explain, and there are quite a few in the field, particularly these ones on the bottom right, that from Lee and Ho, and also used by Hector Arce in other papers, in which you can explain these outflows as produced by a bubble that is being created by these more stronger and faster moving jets that are collimated jets that are launched closest to the star. Nevertheless, without any sophisticated modeling, we can use the observations from the different CO isotopologues to try to estimate the optical depth and hence in turn the opacity, and derive accurate estimates of the mass loss and momentum and other outflow properties, which is what we did with collaborators, with Dario Rodriguez, who's now at JAO. She was former Jansky fellow here at NRAO, and she's the one who did all these opacity calculations to estimate the disk properties, the outflow properties, which in turn seem to be consistent with what you would expect in terms of mass loss rate from other FURI stars, and consistent also with the mass loss rates that are estimated from optical lines. So everything seems to be consistent. Here's a nice gallery that I made a few months ago. Maybe we have a couple of more to add of outflows on FURI types or eruptive stars. So I'm including a few transitional stars. GM-CHA, for instance, at the bottom is a star that has both FUR and XOR properties. So it's now we believe that there isn't really a hard distinction between FUR and XOR, and it's more like a continuous evolution between one class to the other. Now, to wrap up and use the last minutes of the talk, I'm going to show this recent result that seems to hint towards some explanation on what may be rendering FURIs, the prototype star disk unstable, and hence maybe shed some light on what is happening on other eruptive stars. So it was very clear that if we use our estimates from the mass estimates from millimeter observations, even though they were probably wrong because the optical lithium assumption is not right, but that's the grip we had. If we use those, if we use those estimates, a FURI disk should be evaporated in less than 100 years because the disk is accreting at 10 to the minus 4, 10 to the minus 5 solar masses per year, right? And we measured masses of those orders of magnitude. So something else must be replenishing the disk, or the disk would evaporate. And if you look at the star with high resolution, like this scatter light image that you see in the left from Haichao, from Subaru telescope in Hawaii, you see that there is still a lot of material surrounding FUR itself. You have this sort of arc-looking. You don't see a lot in that image because the signal to noise is not too good, but there is something going on, okay, in scatter light at least. And also, if we look at the kinematics of 12CO taken with the 12-meter array, this is still the cycle 0 data that we published in 2015. You see that there is a hint of rotation, but it's more than just rotation, okay? And there's something going on. And I don't know if you can see my cursor, but I want to point you to the second row here, okay, to velocity of 10 to the 10.3, 10.5. There is this elongated feature going to the south, right? You see in 10.15, you see it very clearly. There's something elongated to the bottom. But at the time, we had no idea how to interpret this image, okay? So, especially that feature, it was early years of ALMA, so there wasn't, it could have been something instrumental. So we didn't discuss that in that paper because we didn't know very much what to say of it. So we did some modelings of the rotation. We said, well, if we had interactive disks, we ran some really nice hydro simulations and did some predictions of what sort of velocity maps we should see if the outbursts were actually caused by this interaction between the binaries, and got some more data, which is some of the data you saw already in the high resolutions data you saw on the continuum. But here I'm going to show you what it changes if you have, well, twice the number of antennas and twice the integration. So now we got a better view of the kinematics in 12CO, a better view of the kinematics in 13CO, but we still couldn't make much sense of it because it's a very complex kinematics compared to really nice Keplerian disks, which is what we study in class 2s. So time had to pass before we could actually understand what was going on. But one interesting thing is that what we saw in cycle 0 as that elongated feature going to the south was confirmed in these higher sensitivity observations. And we also got better scatter light images. This is the Haichao image I showed you before, and this is the sphere image of the same scatter light, seen by Haichao, but now in much better sensitivity and resolution. This is data that Alice Surlo is publishing at the moment. I think the paper just got accepted. But I mean, this still needs to be interpreted. So some people see this as an outflow emanating from the star. Some people want to interpret it as an inflow of material falling into the star. So which one is it? We were able at least to zoom into the star and see that some of the material, as you can see, so I'm gonna. We were able to zoom into the star and see that some of the material, some of the gas is following Keplerian rotation around the primary, which is what you see on the right. But on the left, you see that some of the blue shifted emission seems to follow this arch. So we're still trying, we still have data in hand that we're trying to put together with models to see whether this kinematics is following the arch and whether it's accretion or not. Because from the modeling, you can see here, these are the models I was telling you from Daniel Price and Nicolas Cuello of binary interactions, and you see that you would expect some very messy kinematics from this. But as I was saying, we spent a lot of years trying to understand this, and models have become more sophisticated. We've got this very comprehensive view of the FURI system from the very large-scale outflows all the way to the inner regions of the disk, and to detect this smoking gun of viscous accretion in the midplane of the disk. And we were happy with that. But what was really popular last year at Protostars and Planets was this: accretion streamers detected in young stellar objects. And many papers have been put forward, and there's also a very nice review by my former university classmate, Jaime Pineda, and his group, and many other groups that have been detected these sort of features in ALMA data in different molecules at different stellar stages, all of them young. And all of this can be interpreted by a stream of material coming from the envelope and falling into the disk, right? Or into the inner regions of the young stellar system. And I remember seeing all these posters and seeing these presentations, and they were all reminiscent to what we were seeing in FURI, that what we had seen in cycle 0 and in our follow-up observations. So it was very fortuitous that we didn't publish this data earlier, because now we had a theoretical framework that we could test. Can this linear feature be explained by an accretion streamer? And we used TIPSI. TIPSI is it's a modeling code developed by Ashish Gupta and Anna Miotello and other people at ISO in Garching. And it turns out it can be very well modeled by a stream of matter accreting into star following the trajectory that you see on the right or on the left, okay? And also using the different isotopologues that we have, we can have an estimation of the mass accretion rate. So to answer questions, can this streamer sustain the current outburst? Or other question, can the streamer be massive enough to render the disk unstable and hence trigger the accretions? So we got a very low accretion rate, 10 to the minus 11. Let you remind you that in outbursts, these FURI stars are accreting at the rate of 10 to the minus 4, 10 to the minus 5 solar masses per year. So the disk itself can certainly not, sorry, the stream itself can certainly not sustain the accretion rate, but whether it can render the disk unstable, that's something that modelers need to work on right now. We left a segue in the paper calling for modelers, and it was really nice because I've got emails from 3 different modelers asking me for the data in the past week. And even if the streamer is not capable of rendering the disk unstable right now, this is the first time we see evidence, active evidence of active accretion still ongoing from an envelope into the disk on an eruptive star. And this was picked up by recent authors. this paper came out, it hasn't even come out. It was submitted this month to archive, mainly led by Miriam Minesti and Sean Andrews, in which they try to highlight the importance of these accretion streamers that we've recently discovered into regulating the planet formation process. So this is a new field, basically. There's an open canvas, a wide canvas here for developing and refining our paradigm of star formation. So I invite you to please check this paper on archive or when it becomes published. So with this context and the potential impact, we got this very nice press release. We work with I got the pleasure to work with NRAO's graphics designer and so what you see here is on the top, right? On the top, you see this artist's impression of what is going on in the a priori binary system, and this nice accretion streamer coming from the southeast. And with that, I'm going to leave you with this animation that we put in social network that incidentally has the music that Patricia was referring earlier on. This is sounds created with the ALMA data from Orion, taken from cycle 0. We took the spectral line data, we made sound banks, and we gave it to the music community. And the music that you hear is one of the pieces that we got back. So as you can see, we've been observing Orion for a long time with ALMA. And I think we will continue observing it for many years to come, especially with the wideband sensitivity upgrade that some of you may have heard of, that is keeping us very busy these days at ALMA. It's going to be keeping us very busy for a couple of years more. And that will double the bandwidth and will increase the sensitivity of ALMA and will open new discoveries and hopefully many serendipitous discoveries that we didn't expect, like the discoveries of these streamers around young stars and around a priori type stars. So before I open the floor for questions, I wanted to highlight that we are organizing an international workshop in Chile in September. Very nice time of the year to visit Chile. It's beginning of spring over there. And we're going to be discussing eruptive stars in the context of planet formation. Registrations is still open. We have financial support for early career students, for early career staff and students. And we look forward to looking for your abstract and your contributions in Chile. So I leave you there. You can Google it. Burning Fire is a very catchy name. So you should be able to find the webpage easily. And with that, I'll leave my summary and open the floor for questions. Thank you very, very much.
Thank you very much, Antonio. Amazing talk and very impressive picture and images. And we have time for questions. Well, I'm not an expert on this, but I was wondering what is the role of the magnetic field in the accretion process in outburst phenomenon?
Not an expert myself, but a very, very pertinent question, Enrica. Thank you very much. Well, it's again, I'm not an expert, but where I know it comes through, and I think I mentioned it briefly. And as you know, we believe that magnetospheric accretion is what regulates the accretion in class 2 disks, at least. And the XOR behavior is probably linked to that, because we still believe that the material may be piled up, but it's still funneled through the accretion, through the magnetic field onto the star. The outflows themselves, at least the very large scale wide opening angle outflows, are also believed to be launched at larger radii. So they don't come from the collimated jet, but they're probably the magnetically driven outflows that are launched further away from the star, at relatively larger already. And of course, and this is something that people are working on right now, trying to understand the magnetic fields of class 0 protostars and understand how they can collapse and how that leads to some sort of regulation is something that's still work in progress. And it's something that we're really hoping that the enhanced sensitivity of ALMA 2030 will allow to measure better the magnetic fields, because we've done a lot of things in terms of studying magnetic fields of young disks and young protostars, but we're still fighting sensitivity in many areas.
So you also find the radio jet emission in both the classes FUR and XORs.
Yeah, we see more ejection in the FUR one, which is a more energetic counterparts, but,
Okay.
but in both, obviously, the magnetic fields are playing a very important role in regulating the accretion.
And SKA could shed some light on the characterization of the disk chemistry or the outflow as well.
Don't know, and even though I am at the National Radio Astronomy Observatory sitting right now, my field is a little bit oriented towards the millimeter observations, just because the disks are not so bright in those regions. We're pushing the limits of current instrumentation by going to lower frequencies, but from the disk point of view, we're trying to, as you well know, we're trying to study not trying to study, but most of the science output at those frequencies are related to larger grains, trying to see how those pebbles, centimeter-sized pebbles, can turn into planets. And but as you go to lower frequency, you're also fighting other non-thermal processes. Right? Stars have winds, so you see a lot of free emission, and you also have well, potentially spinning dust and other things that can affect your observations.
Okay. Well, if there are no questions, I have another one. I was wondering, do you find a typical size of the outflow in these two kind of objects? Maybe in the few are more extended and in the XORs are more compact, or you don't find any trend between these two classes?
We don't find any outflows in the XORs. So the picture is the XORs being practically class 2 disks, protoplanetary disks like classical T-Tauri stars or HL taus. No, actually, HL taus is not a good example. Yeah, if you compare the spectral energy distributions of the two type of stars, one of them resembles way more of just a disk and a star, and the other one a disk and a star and something else. So FURs have a little bit of envelope and also outflow, whereas the XORs are probably just stars with a disk that are becoming unstable in shorter timescales and smaller intensities also.
Okay. And along with the CO and the other isotopolog you mentioned before, do you use other high density tracer which can help to better characterize the disk, for example, disk chemistry?
Well, that is an excellent question, and that's one of the topics we want to cover during the conference. It's the effects of episodic accretion of stellar variability in the disk chemistry, right? Because I've mentioned it very briefly, but we have seen by studying some of these stars at high resolution that during the outbursts, the snow lines migrate, as you would expect, right? If you're increasing the stellar flux by 1,000, right? All the disks is coming bright, much hotter. So the ice lines of different molecules, they shift. And we measure the shift of the water line, which in turn is very interesting because some simulations show that, for instance, grain coagulation becomes more efficiently where you had snow, where you had snow, where you had. So if you have dust grains that were never coated with snow, but you have dust grains that were coated with snow, the ones that were previously coated with snow will coagulate more efficiently in terms of making plant formation more efficient. So that's just from a plant formation point of view. But of course, this chemistry will also be altered. And this is something that's actually starting to happen. There is a PhD candidate here at the University of Virginia, and she presented at the ALMA 10-year conference in this last December some very nice results of line variability on M-type stars that are also very active in their atmospheres. So not even eruptive stars, just normal stars, main sequence stars that are a bit more active than our sun. And she showed that, so they were targeted with Chandra, I think, to find stars in the field that were flaring. And immediately we will follow that up with ALMA, trying to observe within 24 hours of the detection of the flare to make sure that the stars is flaring at the time, and compare that with observations taken a day after, a week after, a month after, and in quiescence. And there is a lot going on. That's all I can say. It's not precisely my field, but I'm very excited of seeing these results and very excited of what in the future may lie in the effects of stellar variability in shaping the architecture of planetary systems.
Good luck.
Thank you. So please distribute to anybody who may be interested the conference details.
Sure.
I didn't say we will have a hybrid attendance. We know Chile is kind of a long way, and September is the beginning of the term in the northern hemisphere, so not a great time for traveling 10 kilometers, but we'll have a very nice hybrid setup for anybody who's interested.
Okay, thank you. And so if there are no more questions, I think we can stop here. Thank you very much, Antonio. And thank you very much, everyone, for joining us. We'll be back in September for a new IPARCOS-UCM.
Thank you very much. Enjoy your summer.
Thank you. You too. Bye.
Bye-bye.
Adiós.